Okay, so more properties about measurability. Okay, so this is going to be something related to your friend's question in the first hour. So if you have a random variable, for instance, if you have a very simple space ABC, and you have a function x of a is 0, x of b is 1, x of c is 2. So there are multiple ways of writing down this function. In other words, there are multiple ways of writing x from omega to somewhere. First of all, I can write this, 0, 1, 2. I can also write maybe integers. I can write the real line or the extended real line. As long as my image space here has all possible values that x can take, each representation, each way of writing x is a correct one. But now comes a question about measurability. So with this, I have the Borel sigma algebra on R bar. With this, I have the Borel sigma algebra on R. With this, maybe I have the power set. And with this, again, I have the power set, 0, 1, 2. These are the natural sigma algebras on each of those sets. Which one is correct? So when we say x is measurable with respect to f, let's say f here is also just the power set of omega, okay? F is the same in all 4 representations, but this sigma algebra on the second space changes. So is there any difference between saying that x is measurable with respect to f and this sigma algebra, or f and this sigma algebra, or f and that sigma algebra? There shouldn't be any difference. Otherwise, we would be into trouble. So let's make sure there is no trouble with that. A sanity check. Okay. So let x omega to e be a function. Okay. So e is, let's say, r bar. Okay, the largest you took. Okay. So let A be a measurable subset of the sigma algebra on E such that x of omega is a subset of A. In other words, x of omega is the set of all possible values. Pick any measurable subset of E that covers all possible values. A can be Z, A can be R, A can be R bar, okay? Or A can be the set itself, okay? Just make sure you pick a measurable one, and then let script A be the trace of script E on A, so that you have this smaller measurable space, the trace space, okay? So here's the claim. X is measurable with respect to f and script E, if and only if x is measurable with respect to f and script A, the trace. Okay, let's prove it. So suppose first that x is measurable with respect to f and script E. And now we're going to show x is measurable with respect to script A. Okay? So recall that script A is sets of the form A intersection D, where D is in E, okay? We just intersect all measurable subsets of E with the smaller set A, okay? So we need to look at an event of this form. An event of this form. Well, A is in script E, D is in script E, therefore their intersection is in script E. So by assumption that X is measurable with respect to script E, this is in F. So that proves the part from up to down, and now the converse. Any questions about this part? So there is, we really need A being measurable, okay, with respect to the grand sigma algebra. So now let's do the other part. So we suppose X is measurable with respect to F and A. So what we need to show is that X is measurable with respect to script E. So let's take any set in script E and look at the event X is in script D. X is in D. Well, what does that mean? X takes values in D. Okay. Maybe D is a huge set, okay, that contains points that are not really attained by X. We know that A covers all possible values of X. So I can just rewrite it as X is in D and also in A. Because that's no new information. We all know that. So since X of omega is always in X of capital omega, which is a subset of A for all omega. So just an additional, not really, let me say it this way, not really a new requirement. It's not really a new requirement. This is already known, okay? This is like saying X is 5 is the same as saying X is 5 and X is a real number, right? X is 5 and X is a real number. And once you write it this way, this is in the trace Therefore, by our assumption, this must be in F, because we're going from here to here. It's measurable with respect to trace. And again, we're done. Okay. Let's apply it. Application. Suppose X takes values in the set x1, x2, etc., which is a subset of the real line or the extended real line. Doesn't really matter. Just a countable set, okay? Like the discrete random variables. Okay? Poisson, 0, 1, 2, 3, etc. Also works with finite. Okay? So now let's take this as A. Okay? And script A is the Borel sigma algebra on A, meaning that the trace of the full Borel sigma algebra on this set A, countable set A. as part of your second homework, you're going to show that this is nothing but the power set of A, the discrete sigma algebra on A. This is something you're going to check. Okay? So, therefore, by previous proposition, X is measurable with respect to the Borel sigma algebra. I'm skipping the F part. If and only if X is measurable with respect to the power set on A, set of all subsets of A. But the set of all subsets of A is really generated by singletons. I think we showed it at some point. So the idea was that, hey, we're dealing with a countable set. Every subset is countable. Therefore, we can always see it as a countable union of singletons. Okay? That was the idea we checked before. So now apply one of the previous propositions today, the one which was about a collection script P generating the sigma algebra on E. Remember that one that we just proved in the first hour. We can even say X is measurable with respect to 2 to A if and only if X equals Xi is measurable for all I. Because these are the sets in the script P set collection, right? So all you have to do is to look at events of this form if you're dealing with a discrete random variable. Therefore, whenever we say that a numerical random variable is measurable, you can always understand it as measurability with respect to the Borel sigma algebra. But if you have discrete ones, if you have random variables taking only countably many values, this is the same as considering the power set on the countable set of values. Okay? So there is no ambiguity. No ambiguity. Okay, let's define such a discrete random variable. That's going to be the simplest type of discrete random variable. We have omega f. Okay. So let A be a subset of omega, not necessarily measurable, and define the indicator function of A by this. So it's a function associated to A, okay? And it is defined omega by omega as follows. It is 1 if omega is in A. It is 0 if omega is in A complement. So you have your omega, you have your A. Your random variable takes the value 1 here. It takes the value 0 everywhere else. Just 2 events. So now, let me just say it as a lemma, okay? Indicator A is a random variable, meaning that it is measurable, if and only if A is measurable. A is an F. Let me put a star here, the thing that we have just discussed. Use star Okay? What does that mean? You have a random variable taking only two values, 0 and 1. So to check the measurability of it, just look at the events. It takes the value 1. It takes the value 0. What are those events? What are those events? What is the event that this is 1? A. And this is its complement. It's that easy, right? Just on this picture, it's clear. So if indicator A is measurable, we have A is measurable, and also A complement is measurable, but this is for free. If A itself is a measurable set, then we have, then A complement is also measurable, so that both of the two events are measurable. Okay. Okay, so let me give names of this random variable. So there are a few ways of naming it. So indicator function of A, or if you're in the probabilistic setting, you call it a Bernoulli random variable associated with A, event A. It's the random version of binary variables, right? 0, 1. Okay, any questions so far? So that's going to be the building block of all random variables. Let's say numerical ones, okay? All numerical random variables. That's the simplest random variable. So what was the simplest measure? What was the simplest measure? Probability measure, which was also like 0 and 1. Anybody remembers? Dirac, yeah. So Dirac was the simplest measure, and indicator, or Bernoulli, is the simplest random variable. So it's the building block of all random variables. And our aim is to work towards this hypothesis, okay? Indicators are the building blocks of all random variables, all numerical random variables. This is our next aim. So what do I mean by building blocks? Well, I mean that if you have two indicators, you should be able to add them. Well, in general, if you have just two random variables, you should be able to add them and get a new random variable. So in other words, measurability should be preserved, should be something that is preserved when you take some usual operations like addition, multiplication, division, etc., etc. Okay, squaring, cubing, square root, right? Exponentiation, logarithm. So all those operations, when you apply them to random variables, they should preserve measurability. Okay? So this is our next goal. Can we do calculations with random variables? Let's say numerical random variables. Numerical variables. Okay. So here's some recall or some conventions. So I always say numerical, but not real valued, because time to time we're going to need random variables taking values plus infinity or minus infinity. So I don't want to exclude them from our theory. We're building the theory now. So I don't want to exclude them from the theory. So that's why I always say numerical, and this always means R bar valued, okay? So there are a couple of problems dealing with plus infinity and minus infinity. Well, for instance, there is no problem if you add x plus infinity. You just get plus infinity if x is not minus infinity. Okay? X is here just an extended real number, okay? So as long as it's not minus infinity, there is no problem. So minus 5 plus infinity is plus infinity. Plus infinity is also plus infinity. So there is no ambiguity about it. Same for x plus minus infinity. If x is not equal to plus infinity now. Okay? So plus infinity plus minus infinity is undefined and avoid it. Okay? We're going to avoid it all the time. So that's one issue about dealing with numerical ones instead of restricting ourselves to real valued ones. So this is perhaps the biggest issue with those extended reals. And we're going to find ways to avoid them. Okay. How about multiplication? How about multiplication? So if you have x times plus infinity, you get plus infinity if x is non-zero, positive, or plus infinity itself. It is minus infinity if x is negative, including minus infinity, up to 0. Well, what happens with 0? Convention in measure and probability theories is that 0 times plus infinity or 0 times minus infinity is always 0. This is our convention. Okay? So don't leave it undefined. It is always 0. That's how it works. And finally, we should also avoid division by 0. For obvious reasons, 1 over x is a function like this. So if you approach from the positive part, it is going to plus infinity. If you approach it from the negative part, it is going down towards minus infinity. So let's not call it plus infinity or minus infinity, okay? So this is nothing about randomness, right? This is just about numbers. But at least we can apply it omega by omega to operations about random variables. Okay? So we do operations between random variables in an omega-wise manner. For instance, x plus y means x plus y at omega is defined as x of omega plus y of omega for every omega. Okay? Let me also say similarly, x is less than y means x of omega is less than y of omega for all omega. And the event x is less than y means the set of all omega for which x of omega is less than y of omega. So if you write it as a statement without the parentheses, this means it is true for every omega. But if you state it as an event, this is the set of outcomes for which this happens. Okay? It's probabilistic notation. So now that we fixed this notation, let's prove some basic rules, okay, about calculus of random variables, calculations with random variables. Okay, so let's say xy random variables, numerical random variables, okay? Okay. So first rule is going to be this. If you have a deterministic random variable, if you have a constant function, it is always measurable. It is always a random variable. A constant function is a random variable. So what do I mean? Suppose there is C such that x of omega is C for all omega, then all you need to check is that x equals C thanks to this result, right? That's a discrete random variable. It just takes one value, which is C. So all you need to check is that this is a measurable set. And luckily, this always takes this value, so it is equal to omega. So it's in F. That's the simplest one. Now, second one, we said we have two random variables. So x plus y is a random variable whenever well-defined. Whenever well-defined means you never have the case where you get x of omega plus y of omega gives you something like infinity minus infinity. So if infinity minus infinity is always avoided, then this is a valid operation. X plus y is well-defined, and this is a random variable. Let's prove it. Okay, so let's take a real number a and show x plus y is less than a is in F. Because this is something we can do. That's one of the ways of checking the measurability of a numerical random variable, right? Because intervals of the form minus infinity to a excluded, they form a collection of sets generating the Borel-Sigma algebra on the real line or extended real line. So it is enough to show this. It is enough to show this. So the idea here, use the measurability of x and y by separating x and y in the statement x plus y is less than 0. So if you give me an event just about x, I know it's measurable. If you give me an event just about y, I know it's measurable. Now we have to combine the two. Because now we're interested in an event that is about x and y together. Okay, so let's try to write it. X plus y is less than a. And my goal is to separate x and y. Well, let's give it a try. Let's write it this way. At least they are on the different sides of the inequality. But this is, of course, nonsense, right? It is still about x and y together. Okay? So can I further separate x and a minus y? What does it mean to have x and a minus y are distinct values? So x of omega is here. A minus y of omega is here. There is a gap between them, right? What does that mean? What does that mean? For instance, is there a natural number in between? Maybe not, right? If it's 1.1 and if it's 1.2, there is no natural number. But is there certainly there is a real number, right? Are there irrationals there? Are there rationals there? For sure there are rationals there. Why do I insist on rationals? There are countably many rationals. So if I have this, it is the same as saying that there is some rational for which it is in between these two values. So for sure, in any interval, there are countably many rationals and uncountably many irrationals, of course. So if you don't believe this equality, check it more carefully yourself. If you don't believe this. On a picture, it's pretty much clear. But I did not check it like this is a subset of this and this is a subset of that. So I leave it to you. Okay? But once you believe this, the rest is not very difficult. So what do we have so far? X plus y is less than a is the union of q's of, what does that mean? So this means x is less than q and y is less than a minus q. So now we separate it. We separate it because x is measurable, so this is an f. Y is measurable, that's just a number, that's an f. Their intersection is an f. Countable union of sets in f is an f. So we're also done with the measurability of x plus y. So you can add two random variables. What else would you like to do? You have two random variables. What would you like to do with them? You add them. You multiply them, right? And maybe you also want to multiply them with just numbers, right? X and 2x. So maybe I should use it there. So let's see, be an extended real number. Then c times x is a random variable. Is a random variable. I leave it as an exercise, okay? So it's not very difficult, but you need to consider the cases where c is positive and negative and maybe plus infinity, etc., etc. And if you can multiply random variables by numbers, and if you can add two random variables, you can do it in a more general manner. So let a be two numbers. Then ax plus by is a random variable whenever well-defined. Whenever well-defined. And the proof of this is just a combination of parts b and c. Use b and c. Because a times x comes from here. B times y comes from here. Their addition comes from here. Okay, so the next is product. Or maybe first square. X squared is a random variable. Let's prove it. So let b be a real number. Okay, so if b is negative, then x squared is less than b is the empty set, right? Square cannot be negative, which is measurable. If b is positive, then x squared less than b is nothing but it is between the square root of the negative and positive square roots of b, which is measurable because this means x takes values in an interval. So we want to prove the measurability of x squared. We reduce it down to the measurability of x events about the random variable x, which we know to be measurable. So this is also done. Okay, just interrupt whenever you have questions, okay? So now product. X times y is a random variable. I won't say whenever well-defined, because it's always well-defined. Plus infinity times minus infinity is also minus infinity. So, and 0 times whatever is 0. Okay? Always well-defined. So, So there is a reason for squeezing x squared here. So to prove x times y is measurable, I'd like to use that squaring is something that preserves measurability, and addition is also something that preserves measurability. Can you relate x times y with, for instance, x plus y? How? So if you look at x plus y squared and x minus y squared, and if you subtract the two, right, what do you get? You have 2xy and minus 2xy's, so 4xy's. Let's divide by 4. But that's not a problem for us, so that's x times y. And now we're done. Now we're done because x plus y is measurable. X minus y is measurable from here. Okay? Squaring preserves measurability. Divide by 4. Where is it? It's here. Divide by 4 is here. So we're done. There is an error in this proof, in this expression. Who will tell? Think about extended reals. What may go wrong? I said x plus y, x times y, always well-defined. What's wrong in this expression? Yes? X minus y. What if you have problematic when x of omega is equal to y of omega equals plus infinity? Problematic if x of omega is equal to minus y of omega equals plus infinity, or minus infinity, etc., etc. So there are situations where this is wrong. So let's say we have this if y is real valued. So a real number plus an extended real number is always well-defined, because one of the things is finite, so you never have infinity minus infinity, so you avoid it. So therefore, as case 1, assume y is real valued. We're done by this double star. I remember I had some star over there, so that's why I introduced double star. Anyway, and I'm going to leave the problematic part for you. So consider the general case. And write down the two cases. First case is when you have y is real valued. Second case, y is not real valued. So it is either plus infinity or minus infinity. Check that this equation is correct all the time. This indicator is just one minus of this indicator because these are complements. Let me write it. Note, indicator A plus indicator A complement is indicator omega, which is always 1. So exercise, complete this part of the proof by using case 1. But it's important to notice that there is a problem with this expression, okay? When you deal with extended reals. So this is not always correct. This is correct when at least one of them is real valued. Or you always avoid this infinity minus infinity situation. Okay. There are a few more, like 1 over x, x over y, etc., etc. So 1 over x is a random variable, assuming it is well defined, meaning that x of omega is non-zero for all omega. Okay. How does that follow? Well, let me leave it as an exercise, okay? Again, you need to consider the cases where x is positive, x is negative, etc., to write down some expressions, okay? And finally, there is x over y is a random variable, assuming, again, it is well defined. Well, assuming y is non-zero would have been enough, I guess, right? We also don't want infinity over infinity. Okay, let's say it is just well defined. Okay, so the proof would be just from part F and part G, right? Use F and G. And that's the end of my list, but you will see later, either in the course, in the lectures, or in the exercises, that more to come. So x to n, e to x, log of x, assuming x is positive, okay? Log of x, cosine x, sine x, etc. are random variables. In fact, there is a more general result, which we're going to see only at the very end of the course, that if you apply any continuous function to x, it's going to be measurable. But for now, we don't know it. We don't know it. Okay. I'd like to just illustrate all these using an example. Well, an important example. So remember that the indicator function is the simplest type of a random variable. It's Bernoulli. So what can you do with Bernoullis? If you have a bunch of indicators, what can you do with them? So now you learned a lot of operations. So what can you do with them? You can just add them, right? Multiply them by numbers, add them again, and so on. And they're going to give you random variables taking only finitely many values. Okay? So let's define something which we're going to call a simple function. So a simple function is a function x from omega to r. Okay, I don't allow for extended reals here. Of the form x sum of ai times indicator capital AIs for some a1 to an reals, a1 to an measurable sets, and a finite number, integer n. Okay, that's the definition of a simple function. By, where is addition? Part B, and where is, well, let me just say by part D here. By part D of the previous proposition, simple functions are measurable. Simple functions are automatically measurable. So no worries about measurable functions. And that's an application, that's an example where we really use those operations that we just learned, and they preserve measurability. Okay? So let me just draw a picture, maybe an example, okay? Let's say you have a picture like this, A1, A2, okay? And you have X, which is A1, indicator A1, A2, indicator A2. Okay, what does that mean? What does that mean? So if you are in this region, be careful about which indicators give you 1. So if I'm only here in this set difference, A1 minus A2, this indicator is going to give me 1, whereas this indicator is going to give me 0. Therefore, in this region, the value will be A1, and similarly, in this region, the value will be A2. However, I have to be careful about their intersection, where both indicators give me 1, therefore it is A1 plus A2. And according to this formula, outside the union of A1 and A2, I have just 0. No number comes, right? A1 times 0, A2 times 0, just 0. So the thing is that I can rewrite it in many different ways. Many different ways. Why? For instance, I can write A1 indicator A1 minus A2, A2 indicator A2 minus A1, A1 plus A2 indicator intersection, and 0 outside. I can write it as A1 times indicator A1 Oh, maybe even not. I already did it. Okay. Let's do this. Let's say I have A1 all over the union, okay? All over the union. But now I have to add A2 minus A1 if I'm in A2. Is that right? In the difference. But how am I going to get A1 plus A2 in the intersection? A2 for the intersection. Thank you. And this should be correct, right? 0? Yeah? So it's done, right? It's correct. Check that it's correct. Otherwise, you can correct it easily. Anyway, the message is that there are many ways of writing it. Okay? And there is one which is canonical, standard. And it is this one. Canonical representation. Why do I call it canonical? Because the sets in this list form a partition of, so A1 minus A2, A2 minus A1, A1 intersection A2, and everything outside form a partition of omega. Okay, let me state it as a definition, and then we're going to stop at that point. So let x be a random variable taking only finitely many values, say x1 to xm, okay? Then we may write it as x I indicator x equals xi. So these are distinct values, by the way. 1 to m, okay, is called the canonical representation of x. Because these are disjoint sets, and their union gives us omega itself, so they form a partition, and we call it a canonical representation of x. Such a representation is unique. So, okay. Next is take limits of simple functions to approximate all random variables, all numerical random variables. This is going to be our next aim. So now, today we just did the case where we have only finitely many values, okay, simple functions. These are like your discrete random variables. So next time, we're going to take their limits to approximate any type of random variable, numerical random variable. Okay? So thank you, and see you on Friday.